In this lecture, I want to introduce you to the concepts behind text preprocessing. In the previous lecture, we learned that, obviously, you can't multiply words by numbers, which doesn't make any sense. In order to use deep learning, which really means neural networks, we must have numbers, because a neural network is basically just a series of multiplications and additions. So the question now becomes, how do I turn my text into numbers? Specifically, we need the kind of numbers that can be passed into an embedding layer, which means we need integers that correspond to rows in an embedding matrix. Let's start from basic and hopefully pretty obvious points. First, how is text stored? The answer is text files. To be clear, I mean plain text files and not Microsoft Word or anything like that. Hopefully you've done enough Python so that you know how to open a text file, read its contents line by line, and so forth. Hopefully you know that Python files are themselves text files. So text files are a fundamental ingredient of computer programming. You should love them. Okay, so let's say I read in a plain text file using Python. How are those file contents represented in Python code? Well, the answer is as a string. But wait, if the whole file is a string, how can I get the individual words and sentences? Remember that in order to convert my words into word vectors, those words must be represented individually as integers. But starting out, I have nothing but a humongous string full of multiple sentences and each sentence containing multiple words. No good. Okay, I'll make it a little easier on you. Suppose we impose some structure on our text file. Let's make it a CSV. We've all seen CSVs before, so I hope there's no need to explain what these are. Let's suppose, since this is what we're going to see later anyway, that this is a two-column CSV, where the first column is some string representing an email or a tweet that we want to classify, and the second column is its corresponding label. This makes things slightly easier because each line of the file consists of only two parts, an email or a tweet, and some corresponding label. As a side note, sometimes people, including myself, will refer to these emails or tweets simply as documents. That might be confusing to you as a beginner because you might think of a document as an entire file, like a book or a report. But in NLP, when we say document, that probably just refers to a single sample, which could be a sentence or maybe a few sentences. It could possibly be longer, but that depends on the task you're doing. So be aware that the word document is kind of an overloaded term in NLP. It doesn't mean a document as an entire file, like a Word document. It just means a single sample in your dataset. So from here on out, when I say the word document, I'm going to assume you understand what I'm talking about. Now that our data is in the form of a CSV, maybe we can use pandas to load it into a data frame. But the problem is, each of the cells in the first column of this data frame are still documents. They contain multiple words, when what we really want is individual words. In the next portion of this lecture, I want to discuss how we might process these documents in pure Python code to give you an understanding of how this works and how you might implement it yourself. In the end, we're going to end up using a library that's part of the PyTorch ecosystem, but it's quite immature and limited in its capabilities. So it's entirely likely that in the future, it may not fit your needs, and you may need to write your own text preprocessing code. So it's good to have some idea of how this works. In my more advanced and in-depth NLP courses, we actually go over how to do text preprocessing in Python. So if you're interested in getting practice with that, you can ask me about it on the Q&A. In any case, let's start with what we have, a document which contains multiple words and possibly multiple sentences. We know that we want to split this up into individual words. This is a process called tokenization. If you wanted to take the simplest possible approach, you could achieve this by taking your document, which is a string, and just calling the split function. This is probably fine in a lot of cases, but there are some downsides to this too, such as that it doesn't take care of punctuation. Consider the document. Today I walked my dog chased a rabbit. We see here that although the word dog appears twice, the 2 times it appears are different because the first time there's a period appended at the end. So if you wanted to, say, assign a unique integer to each word that appears in your dataset, these would appear as 2 distinct words. That's possibly not good. So you may want to have some code that removes punctuation. You might also want to downcase all the letters as well, although there have been models that kept the original casing. Let's suppose that we've made it to the next stage, where we have successfully tokenized all our documents, so that instead of just single strings, they now appear as lists of strings, where each string is an individual word. As you know, the next step is to convert these words, as strings, into an integer representation. Clearly, each word must have a uniquely assigned integer for this to work. So the word A might be assigned the integer 0, AA might be assigned 1, and so on, until we get to the last word in the dictionary, zythum, which might be assigned 1 million. The question is, how do you write this in code? Again, this is all just conceptual for now, but here are some ideas. First, you define some counter called current index, and you make that 0. You also instantiate a set, which keeps track of every word you've seen so far. Then you loop through each word in your corpus. By the way, corpus is just a fancy term for your text dataset. So each time you encounter a word that you haven't seen before, you do 2 things. First, you add this word and the current index, which will be assigned to this word, to a dictionary. We'll call this the word to index dictionary, since the key is a word and the value is its index. Second, we increment the current index by 1, so that the next time we encounter a new word, it will be assigned a new index value. Pretty simple, I hope. One caveat to the previous pseudocode is that, usually, we don't want to start at the index 0. Instead, I propose that we start at the index 2. So why would I want to do that? Well, if you recall, each sentence in our dataset might be of different length. So we need padding. Padding is usually done with zeros, so 0 is typically a reserved number for that use case. But why start at 2 and not 1? Well, remember that we're going to have a train set and a test set. What if our test set contains words that didn't exist in the train set? Then these should be considered unknown words, because we couldn't have learned anything about them during the training process. And so for unknown words, we should assign the index 1. And therefore, we have 2 special indices. 0 represents padding, and 1 represents unknown words. As a side note, in the library we'll use later, called torch text, it actually does the opposite, but obviously that doesn't change the point. So in actuality, 0 is unknown, and 1 is padding. And of course, this is only the case if you use torch text and you don't write this yourself. Okay, so what's the next step? Remember that we would like to have constant length sequences, or at least constant length sequences per batch. So let's suppose we have a batch of sentences, each of different length. The first sentence is 9, 127, and 6. The second sentence is 14, 21. And the third sentence is 99, 500, 187, and 2. Remember, at this point, we've converted each sentence into a list of tokens, which we then converted into a list of integers. Well, we can see that the lengths of these sentences are 5, 2, and 4, respectively. Since the longest sentence has length 5, the 2 shorter sentences would have to be padded to be of length 5. So the second sentence becomes 1421,000, and the third sentence becomes 99, 500, 187, 2, and 0. And so just a reminder, we're using the convention that 0 equals padding, even though this might not be the case in the code. But here's an interesting idea. Instead of padding at the end, why not pad at the beginning? So the second sentence becomes 000, 1421, and the third sentence becomes 099, 500, 187, and 2. In the first case, we call that post-padding because the padding goes at the end of each sentence. And in the case we're considering now, we call it pre-padding because the padding goes at the beginning of each sentence. As a quiz, think about why we might want to choose one over the other. Which one might be better for text classification using RNNs, and why? I'll give you a minute to think about it, or you can pause the video and come back when you're ready. Alright, so hopefully you thought about your answer to the question. Which might be better for text classification using RNNs, pre-padding or post-padding? The answer is pre-padding. In our case, the RNN will read the sequence from left to right, or equivalently, from beginning to end. That's not a problem in and of itself, but recall, what challenges do RNNs face? The main challenge for RNNs is learning long-term dependencies due to the vanishing gradient problem. So if we put padding at the end, what happens? That means if there was any pattern to be learned from the sentence, it's going to appear at the beginning. And if there's tons of padding, say 50 or 100 zeros, then there's a good chance that by the end of all those zeros, the RNN will have completely forgotten what it saw earlier. And due to the vanishing gradient problem, it's going to be very hard for the RNN to learn to capture those patterns that appeared at the beginning of the sentence. Therefore, it's better, if you're doing a many-to-one task in the left to right direction, that you put your padding at the beginning. Okay, so let's summarize all the conceptual steps that need to happen in a text preprocessing pipeline. First, your data might arrive in some weird format, like, for example, it might be a collection of web page URLs or a database table, or you might be using the Twitter API to download tweets as JSON documents. For reasons you'll understand very soon, it'll be convenient if you can format these into a CSV. Second, when you load in your data, whether it's a CSV or not, this data won't be in the form of one string per word. In order to convert each document into a list of strings, where each string contains only a single word or token, we need to perform a process called tokenization. Third, once you have your documents encoded as lists of strings, you need to convert each of those tokens into an integer representation. That means you need to assign or map each token or word to a unique integer. And in addition, you'll need to convert each sentence from a list of strings into a list of corresponding integers. At this point, your dataset consists of nothing but lists of integers. Finally, you'll want to perform padding so that your dataset, or at least each batch, has the same sequence length. I hope that none of these steps seems particularly difficult to write by yourself in Python code. As an exercise, I would strongly recommend writing your own Python code to perform each of these steps. This isn't strictly required for the upcoming example, but it's an extremely useful skill to have, especially if you plan on doing something unique and not covered by the basic use cases in existing libraries.